In one of my videos, I talk about the importance of the consistent implementation of robust compensation methodology in the stamping process engineering phase. In this video instead, I really would like to go a little bit into the details and explore the main factor that must be taken into consideration to successfully compensate the tools. In the, in the graphic that you see over here on the screen, I tried to simplify this process in just three main steps. The first step is the preparation for compensation. Essentially, prerequisites that should be fulfilled to shorten, at the end, the compensation strategy hunt. Prerequisites related to geometry and also to the overall process, as we will see. The second step is the tool compensation itself. Tasks and activities that must be performed to assess different strategy and pick the best one. And the third, which is the final validation. So we run a final check and then we release the geometries for milling. Let's go a little bit deep into some details of all these steps. So before even start thinking about compensation, we have to make sure that what's in the checklist that is over here on the screen has been really checked and validated. We have to check that there is no risk of splits, wrinkles, and so on, so all defects. But we cannot only check this by comparing single values of results with some limit of these parameters. We have also to check the capability of the process to ensure that no defect will occur. In other words, how stable the results are when considering process parameters variability, and that the chances that the limits are actually reached and exceeded are lower than the standards that the quality system did put in place. That's what we are going to do. In other words, we need to check the CPK value. Then we have to ensure compensability. What does it mean? It means that we need to see the magnitude of the springback, which doesn't have to be so big that it may generate backdraft areas or actually destroy some of the features that are in the geometry. And then also the stability of the results again. We are going to modify the shape of the tool, so we want to make sure that springback behavior is consistent, because if that's not the case, the hunt for a successful strategy can really take long and the quality can be unsure. Last but very important thing is the quality of the geometry. The process must be validated by using CAD quality geometries of the tools, so that during the morphing, the quality to validate the strategy is acceptable. Only once we have achieved these goals, we can start looking for compensation. And the first thing that we do when we start looking for compensation is the measurement of the springback, because from that measurement we generate the vector field that will be applied to the initial geometry, right? When you measure the springback, you better pay close attention to the part positioning and the clamping, and what you are measuring in terms of distance from reference or displacement from reference. In the graphic, you see that there can be a slight difference between those, but only the displacement is suitable for compensation. Another important factor is the alignment between the part and the reference geometry. So please pay attention to that. The second thing that we really need to consider is what we are measuring, right? Is what we are measuring to compensate what tool. And this, this is actually the main part of the strategy. May I use the final result to compensate the drawing station or the trimming station, and so on, or the flanging station, and so on and so forth. Plus, as shown again in the graphic, tool and vector field might not be really the same. For instance, if I want to compensate the D20 from the springback of the last operation of the 30 operation, like in this case, you see that the extension of the vector field is broader than the tool itself. So this can generate some issue in the creation of the geometry. And the third thing is the generation of the surface itself. First, you define the regions where the vector field must be applied, and with which compensation factor and smoothing factor. Also, in this case, the results in terms of geometry can be quite different. The final step is the validation of the strategy. Not only the magnitude, but we have also to check the stability of the results. The combination of these two results are combined in what we call process capability or process robustness. Final validation includes the generation of the final CAD quality geometry and the validation of robustness again. When created CAD quality surfaces, we may drift a little bit from the geometry created during the compensation strategy definition. The higher the deviation, the more important is the final validation step. Only when these steps are performed roughly, we recommend to release process and geometries for digital spotting and then milling. At the end, it's also crucial that milling actually replicates as close as possible what was validated, especially in all active surfaces, because if engineers simulated what can be built, now it's time to build what was engineered. Thank you for watching.